đi vô. Next time, baby girl. Dinner time. Dinner. Video keep baby. You. Yeah.
Hey, Aaron, good evening. How are you doing? Yeah, it's the end of the day. This class is so late. Oh man, yeah. So we have a full day of work and then class after this. That's rough. Okay, that's good. That's good. All right, it's 7 o'clock, so let's go ahead and get started. Good evening, everyone. How's everyone doing today?
Good.
Good, good. Glad to hear it. All right, and so today, you know, on Monday, excuse me. So on Monday we did our first ANSYS activity, one of two, unfortunately for this class. But today we're going to be starting on the theory. Okay, and so what you saw on Monday in ANSYS was kind of a big picture kind of look of what finite elements is all about, right? And so finite elements is all about taking a physical situation, you know, and simulating it, you know, to get results like displacements, stresses, and things like that. Okay? Today we're actually going to start talking about, you know, what's the theory of you know, what's going on underneath the hood for all of these for these kinds of situations. Okay. And today we're going to start with a method called the direct stiffness method, and you know, and we'll go from there. Okay. So I don't want to spoil too much or talk about too much, and so you know, we'll kind of see the rest of it in the lecture. Right? So before I get started, I do have an announcement. Okay, so according to the provost, everything is looking good, or everything is looking safe for our return to campus, and so you know, she's going to get her wish, and we're all going to return to campus next week. And so starting next week, I won't be here anymore, which is my apartment. I'll actually be in the classroom giving the lectures. And so, you know, you can come to the lecture room, which I believe is CS 309, and then, you know, actually come to the lectures in person for that. But I will continue on with the Zoom. And so, you know, just like I promised at the beginning of lecture, you know, if you still wish to attend the lectures virtually, you know, I know, you know, for this class in particular, you know, I know a lot of you are working full time, and, you know, it's a little bit difficult to make the drive all the way to campus to, you know, to view the lectures. And so, you know, I plan on continuing on with the Zoom thing just so that, you know, just so that you have that flexibility. So you can either view the lectures virtually, or you can view them, you know, asynchronously by watching the recordings on YouTube. Okay. But for me, myself, you know, I will start going to campus, and you can actually see me there in person. Okay. All right, and so that's it for the announcements. And so, are there any questions I can answer before we get started? Okay. All right. So let's go ahead and get started. Okay. And so the topic for today's lecture, and you know, this is going to be kind of the broader topic for the next few weeks, up until the first midterm, basically, is going to be the direct stiffness method. Okay. Okay. And so, you know, let me start out by saying that, you know, what we know as the finite element method or finite element analysis, there's lots of different ways that you can implement that. Okay. If you can hear that, don't worry. My cat's not dying. She's just, that's her post dinner yowling. But you know, she's fine. I'm not abusing my cat, I promise.
That just makes it sound suspicious, Professor.
Well, you're free to believe what you want. I'll bring her at the end of lecture, just because, you know, this will be the last time I'm at home, so probably the last time we'll get to see her. So I'll bring her at the end just to show you that she's fine. All right. And so I think, you know, this fact is surprising to people, because, you know, when we think of the finite element method, you know, you think that it's just one method, but, you know, the finite element method actually refers to a lot of different, you know, a lot of different kind of direct, you know, a lot of different methods to implement that. So it's kind of actually a more of an umbrella of methods. And so we're going to talk about actually a few different ways to implement that. And so we're going to start with the direct stiffness, which I think is a really good starting point for this, just because it's I think the most physically intuitive way to start this. And it kind of illustrates a lot of key concepts that I want to keep going moving forward. Okay. Okay. I will say though, so I want to be upfront and honest with you guys that the direct stiffness method is not one that's actually used practically in a lot of codes. And so if you kind of looked at the source code of ANSYS, you will see that there's no direct stiffness method in there. And so it's not really a practical. I like to call it, it's not really a practical method in the way that, it's not used to actually solve practical problems. There's not any, commercial codes that implement direct stiffness. And so it's more of an educational kind of method. Okay? But I like to start off with that in this class, because I think it illustrates a lot of key concepts, and it kind of builds us up to some of the more sophisticated methods, which we're going to look at the end of class. Okay. And so that's kind of the motivation of why we use it, or why I'm bringing it up in this class. Okay. A question: so is it not very cost effective, efficient for computing? It's just very limiting in terms of the types of problems that it can do, and so it's very limited to just just straight up beam problems, straight up truss problems, straight up frame problems, and so. The challenge with the direct stiffness method is that you have to rely a lot on what your physical understanding of your system is, and you kind of use that to kind of invent up parts of the method. More traditional finite elements, kind of what you'll see in ANSYS, is that they actually go straight off the governing equations. And so if you have like a differential equation that simulates structures, like what we'll learn later is called the Fullerton method. And so the Fullerton method will actually take that equation and directly, work on that equation, integrate by parts and do a lot of things like that in order to get the finite element form. So the direct and direct stiffness refers to the fact that we kind of directly, estimate some things just based on our physical understanding. And so, that's not always possible given, some complex situations. And so, it's very limiting in that sense. But because of that, it kind of skips a lot of the obtuse and kind of dense mathematics that we'll get into later in the class. But it gives us kind of a good overall picture of what the finite element process is. Okay. And let me go ahead and talk about what those larger kind of steps are. Okay? And so kind of what I want you guys to get from this unit is not really the direct stiffness itself, but kind of the overall steps to implementing a finite element method. Okay? And so there's three kind of main steps that I want you guys to focus on, and we're going to continue doing these three main steps even when we start to do some of the more complex math. Right. All right. So number one, the first step is to compute all the element stiffness matrices. Okay. And I know none of this makes sense now, but it'll make sense later. But I did want to list out the steps here because they are important. All right, step one is to compute all the element stiffness matrices. Step two is a step called assembly, which we'll go over later today. Okay. All right, step three is to apply boundary conditions. Okay. And step four, which is kind of not really a step. I mean, it is a step, but not one that we'll focus on too much, is the actual solution. And so how to solve that. Okay. All right. And so those are the four kind of overall steps I want you guys to focus on from this unit. And and I'll highlight what those steps are and what they all mean as we go throughout the lecture today. Okay. All right, any questions on this so far? Okay, so let's start with the first step, which is the element stiffness matrix. Okay. For now, I'm just going to call it the stiffness matrix. Okay. And so to kind of motivate the what the stiffness matrix is, I'm gonna pull in something from elementary physics. And so hopefully you learned this from your first physics class, no matter how many years ago it was, but hopefully it should ring some bells. Okay. And so what I'm referring to here is Hooke's law for springs. Okay. All right, and so what Hooke's law basically says that if you have a spring, okay, and so I'm going to attach the spring to a wall, okay, and if you pull on the spring, right, and so you pull on the spring with a force F, right, and so F here kind of characterizes how strongly we're pulling the spring with, okay. If the spring had an original length L, so that's kind of the resting length of the spring, what we kind of intuitively expect is that when we pull on the spring with the force F, it's going to lengthen, right? And so it's going to lengthen by an amount, we'll say it's D, okay? And so we can form a relationship between the applied force and the resulting deformation in terms of this, right? And so what we say is that the applied force on a spring is equal to the resulting deformation modulated by a property of the spring itself, right? And if you recall from your physics classes, every spring has something called the spring constant K. Okay. Okay. And so that K there is the spring constant. This F here is an applied force. Okay. And D here is the displacement or deformation of the spring. Okay. Deformation. Okay. All right. And so I want to talk about the role of the spring constant here, because that's kind of key to understanding, what the role of the stiffness matrix is. Okay. And so in this kind of very simple equation, the spring constant plays a very important role. Okay. And that role is to basically act as a proportionality constant that, or you can think of it as almost like a conversion constant that relates the applied force to the deformation. Okay. Okay. And so what the spring constant tells you is that for this particular spring, if you apply a certain amount of force, then it's going to give you this amount of deformation. Okay. And another thing I want to highlight about the spring constant is that it's an inherent property of the spring itself. Okay. Okay. The spring constant does not depend on any external factors. And, I know technically speaking, something like the spring constant, it probably depends on the temperature. And so if you heat up the spring, to a certain degree, the spring constant is going to change, but we're going to neglect all that, okay? And so we're going to assume that the spring constant is something that's inherent to the material that's not going to change, right? And so if you ask the spring on Monday, you ask the spring on Thursday, you ask the spring, when it's taking a bath, when it's, just chilling on the deck, right? The spring constant is going to be the same because it's inherent to them, right? It's the spring constant is the spring constant. Okay. And so what this, very simple formula tells us is that, when you apply, external forces to a physical system, then the properties of that system that are inherent to that system itself, the physical properties, the geometrical properties, it's going to determine how that system responds or how that system is going to deform, in response to those external forces. Okay. And so, I know it kind of feels like I'm making kind of a big deal out of a very simple equation, but that kind of understanding is going to be key to kind of understanding what the stiffness matrix is, in terms of what role it plays for our finite element method. Okay. Okay. Any questions on this so far? Okay. All right. And so that's Hooke's law for a spring that's attached to a wall. But let's generalize this a little bit. And so let's say that, instead of the spring being fixed to the wall on one side, let's kind of change it so that, both ends of the spring can deform.
Professor.
Yep.
So with this spring example, are you basically saying that like our stiffness matrix is going to be the regulator between our force and our total deformation in our system of like analysis that we're applying our conditions to?
Yeah, no, that's kind of exactly where I'm going. And so, the stiffness matrix is basically going to play the role of that spring constant. And so, in kind of finite element worlds, we like to think a lot about, what are our external forces or what are some things that we're applying. And we want to relate that to what, how the system is going to respond. And so things like the deformation and displacement. And so the thing that actually relates those two is going to be the stiffness matrix. So yeah, that's kind of where we're going. Right. Okay, and so let's generalize this. And so, instead of having, just one end of the spring deforming, let's say that we generalize it so both ends can deform. Right, so here's our spring, and now we can grab both ends, right? Right, and so we can set, let's say that, one end of the spring is going to deform by an amount D1, and the second end is going to deform with an amount D2, okay? And to apply this deformation, we can apply forces, okay? And so let's say we have an applied force F1 on one side and applied force F2 on the other side, okay? Okay, and so, because we've generalized this, we've turned this into, instead of having just 1 degree of freedom, instead of having just one force, one deformation, we now have 2 degrees of freedom, right? And so we have, D1 and D2. But they're related to each other, and so they're not totally independent. And so this is now what's called a coupled system. Okay. There's 2 degrees of freedom, but they do depend on each other because they're attached to basically the same spring. Okay. And so, we can generalize this even further. And so if we think about systems that aren't just limited to a single spring, and so if we think about, finite element situations with, hundreds or thousands or even, millions of degrees of freedom, we can have, coupled systems like that as well. Okay. And so, with that in mind, and actually, with kind of the question that Jacob asked, we can kind of generalize this into kind of a very general kind of Hooke's law. Okay. And so Hooke's law was just kind of a single algebraic expression. And so we have a single F is equal to a single spring constant multiplied by a single displacement, right? But the way that we can generalize this is as a basically a matrix set of equations. Okay. And so instead of a single force, what we can have instead is a force vector. Okay. And so now we have F with an arrow on top. Instead of a single spring constant, what we have is, you can think of it as like a matrix of spring constants. Okay. And so that matrix here, this is basically our stiffness matrix. Okay. And then we have our response vector, which for now, I'm going to limit our discussion to just kind of structural cases. And so this would be basically our deformation vector. Okay. And this F right here, this is our force vector. Okay. And so, that very simple kind of Hooke's law equation can kind of generalize into kind of a more general, finite element type relationship where, we have instead of a single force, we have a vector of forces, and we have, a matrix of stiffness constants and a vector of displacement response results. Okay. Okay. And so, the next steps in this lecture is to kind of, derive what that stiffness matrix looks like for a general spring. Okay. But before I go there, I do want to take a moment to kind of talk about just, how this, relatively simple looking system can actually generalize to even more things. Okay. And so finite elements, I know a lot of people think of finite elements as solving structural problems, but it's actually a lot more flexible than that. And so you can actually use finite elements to solve, almost any kind of physical phenomenon, as long as it's governed by a differential equation. But, even if we're talking about things like heat transfer or fluid flow, this interpretation of the, of the stiffness matrix extends to that as well. Okay. Except we're not talking about things like structural stiffness or like forces or deformations. We're instead talking about things like, like temperatures and heat fluxes and things like that. Okay? But the idea stays the same, right? And so remember how I told you that, the stiffness or the spring constant for a spring is an inherent physical property of the spring itself, right? And, no matter what type of equation that you're solving, the stiffness matrix has kind of the same interpretation, right? And so this stiffness matrix here, just in general encapsulates, all different kinds of physical geometrical properties of a material, okay? And so what those properties are, depend on the nature of the equation that you're solving. But, if we're talking about, heat transfer, this would be like the thermal properties of the material. And so things like its thermal conductivity, things like its heat capacity, probably its density too, probably like its thermal diffusivity, all of those things get lumped into the stiffness matrix. Okay. And things like instead of the deformation vector, that would be a temperature. Okay. But to kind of keep things, I think, from getting too confusing, we still adopt the same kind of terminology that we have for structures. And so even if you're solving like a thermal problem or fluids problem, we still call it the stiffness matrix. We still actually call it the forcing vector. I think the only difference is that instead of a deformation vector, we call this the response vector or the solution vector. Right. And so, if you read papers on like thermal finite elements, fluid finite elements, you'll still see terms like stiffness matrix and forcing vector, just because the finite element community has just chosen to adopt those terms for everything. But that's basically what it's referring to. Okay. Any questions on any of this? Okay. All right. And so that's kind of the role of the stiffness matrix in general. But the question, the next kind of question you should ask is, okay, now that I understand what the stiffness matrix physically is, how do we actually determine what goes inside it? Okay. And that's going to be kind of the, we're going to be kind of answering that question, over the next few weeks for, lots of different types of elements. But we'll start with the spring, okay? And so let's look at what the stiffness matrix looks like for a spring element. Okay. And so let me go ahead and write our general spring once again. Okay. Okay. And so for our general spring here, which we're going to pull at the two ends, we have a deformation on both sides of the spring, as well as an applied force on both sides. Okay. And so our entire stiffness system here is going to correspond to a relationship in between those forces and those deformations, right? And so in this case, since we just have 2 degrees of freedom, we're going to have a 2x2 stiffness matrix. Okay. And so this right here is our 2x2 stiffness matrix. Okay. The question now is, what the heck do we even put in these quantities here? Okay. The only thing that we know about the spring is that it has a spring constant K. Okay. And so we need to kind of, work that spring constant into this matrix somehow. Okay. Okay. And so to start that process, let me take this kind of very general situation and kind of narrow it down a little bit. Okay. And so first let's make the assumption that the spring is in static equilibrium. Okay. And so if a spring is in static equilibrium, that means the applied forces on the spring are going to be equal and opposite. Okay. And so let's assume that we have an applied force T on both sides. And I really apologize for this, but my wife kind of locked herself out of the apartment, so I need to go open the door. So I'll be back in 1 minute. Okay, I'm back. I sprinted down as fast as I could. Okay, so we have a equal and opposite force T on both sides of the equation. Okay, they're equal and opposite because the spring has to be in static equilibrium. Okay, but we're still going to assume that the deformations are D1 and D2. Okay. And in fact, this one has to go this way, because we're pointing out in that way. Okay. All right. Okay. And so, now we kind of have this kind of more concrete situation to look at, because we're in static equilibrium. And now let's actually work with this to fill in the stiffness matrix. Okay. Okay. Any questions on this? Okay. All right. And so if we take the situation right here, right, and we want to fill in the stiffness matrix, let's actually use what we know about springs. And so let's apply Hooke's law to this kind of static equilibrium situation. And so in this situation, even though we're applying a force T on both sides, we kind of sum it up as just a single force T. Okay. this is equal to the spring constant multiplied by delta, right? Where this delta right here is the total deformation of the spring. We can come up with another expression for this deformation based on the nodal deformations. Okay. Okay. And so if we go back to the figure on the previous page, we can see that if we apply an equal and opposite, in this case is a tensile force T on both sides, then we're going to have D2 that's going to the right and D1 that's going to the left, right? And so the total deformation that we have is just going to be the difference of the displacements of those nodal deformations. Okay. Okay. And so we basically have delta is equal to D2 minus D1, okay? Right? Because remember, D2, D1 are basically a measure of how each of the two ends of the spring deform. And so if we take their difference, then that measures how much the spring is deforming overall, okay? All right, so let's go ahead and plug this in over here. And so if we plug that in for delta, what we get is T is equal to K times D2 minus D1. Okay. All right. Okay. So this is good. And so we've basically used Hooke's law, and we're able to incorporate D2 and D1 into our equations. Okay. All right. And so now let's use this equation to incorporate F1 and F2. Okay. Okay, because remember, if we looked at our general stiffness system here on the other page, our general stiffness system is a relationship between F1, F2, and D1, D2. Okay, and so we're about halfway there, and so we have D1 and D2 in our equation here, but we need to account for F1, F2. Okay. All right, and so to find how F1 and F2 are related to this, let's compare our two figures here. Right. And so we can see, in kind of our general figure up here at the top of the page, we can see that F1 and F2 are applied on the two nodes of our spring, and they're applied to the right, right? If we compare that to, the bottom here where we made the assumption of static equilibrium, we can see that F2 and T are, in this case, exactly the same, okay? F1 and T, they have the same magnitude, but they're in opposite directions, right? And so, the relationship that we can make is that F1 is actually going to be equal to minus T, while F2 is equal to positive T, right? In order for these two diagrams to be equivalent, okay? And so what we can say is that F1 is equal to minus T, and F2 is equal to positive T. All right. And so we're almost done with the derivation. And so the last step of this derivation is that, now that we have these relationships here, okay, we want to eliminate T from these equations because, T doesn't appear in our stiffness system at all, okay? And so in order to eliminate T, all we have to do is just plug in this expression here for T right here and right here, okay? And then we'll have two equations, one of them that relates F1 to D1 and D2, and another equation that relates F2 to D1, D2, okay? And those two equations are going to form the basis of our stiffness system for spring, okay? All right, any questions on this? Okay. All right, so let me go ahead and finish up this derivation on the next page then. Okay. And so if we plug in for t in those expressions, right? And so we have f1 is equal to minus k d2 minus d1. Okay. And we have f2 is equal to k times d2 minus d1. Okay. I'm going to manipulate the terms a little bit here just to make it, just to make it a little bit easier to plug into the matrix. Okay. And so for f1, I'm just going to distribute that negative throughout the parentheses. Okay. And so we're going to have k times. Actually, let me do this just to make it even more clear. And so if I distribute that negative k throughout the entire, throughout the entire parentheses, what I get is k d1 minus k d2. Okay. And f2, I'm going to, just kind of flip the terms. And so just to make sure that d1 is in front. Okay. So we have a minus k d1 plus k d2. Okay. All right, so now that we have these two equations, we can just, all we have to do now is just put them in matrix form, and we'll see that it's going to match up with our stiffness system exactly. Okay, and so when we put this in matrix form, all we have to do is just kind of extract the coefficients in front of the d1s and d2s. Okay. Right, so we have f1, f2. Right, if we pull out the coefficients, we have k, we have minus k, k. Okay, we have d1 and d2. Okay, and there's our stiffness system for a spring. Okay, if we just extract just the stiffness matrix itself, right, and so we just pull this out, then what we get is we get a matrix of k minus k minus k, k. Okay. What the fuck? Freaking app froze on me. Oh my God. I'm sorry, everybody. Okay. There we go. Okay. All right, so we have k minus k minus k, k, right? And so this right here is the element stiffness matrix for a spring. Okay. Right. And so you can see that the only property that we have included in here is k. It's just positive and negative versions of the k. But that makes sense because remember the element stiffness matrix here. No matter what kind of problem that you're doing, it consists of purely inherent properties of the system itself. Okay. Material, geometric properties, all that jazz. For a spring, there's really only one property that a spring has, and that's the spring constant. And so it makes sense that that's the only contribution here to the stiffness matrix. Okay. Okay. Any questions on this?
Professor, does this apply to all situations involving a spring, or only this situation where it's in static equilibrium?
And so, for just for kind of the purpose of this class, we're mostly going to consider just static situations, and so this will apply to all those static situations. Yeah. But if you do have unsteady situations, then that's going to change things a little bit. But the way that we do unsteady situations, and I wish we had kind of more time in the class that we can discuss it. The unsteadiness actually gets added kind of on top of this, and so even though we derive this this stiffness matrix for a static situation, this part here actually makes a big contribution to the unsteadiness as well. But that's kind of a little bit beyond this class. Okay. All right, and so that's part one of the part one of our grand kind of finite element process, which is element stiffness matrix. Okay, and so the next step in the process is assembly, and actually I think the best way to kind of illustrate assembly is through an example. Okay, and this example is going to illustrate to you kind of how all of this fits together, because so far we've only just discussed kind of a single spring. And you can almost think of that as like a single element, okay? But finite elements as a method, works on a huge collection of elements, right? If you remember from our activity on Monday, our plate had, for some of you probably, thousands of elements that are all kind of working together. And so, finding the element stiffness matrices is a big part of the process, but we also have to think about how all the different elements in a grand system overall, how all those are going to interact with each other. Okay, and that part comes in through assembly. And so this section is going to be, an assembly of multi-element systems. Okay, and I think the best way to kind of illustrate this without getting too abstracted mathy is just to do just an example for it. Okay. Right, and so let's consider a situation where we have two springs that are attached to each other. Okay. And so let's say that we have a wall right here, okay? And so let's say that we have spring number 1, spring number 2, okay? And we're going to be pulling on this with a force F, okay? Whereas on the left right here, we're going to fix it to the wall, okay? And so those distinctions are going to be important when we apply the boundary conditions, but let's just focus on just the two springs themselves. Okay? And so let's assume that the first spring here has a spring constant of K sub A. And the second spring here has a spring constant of K sub B. Okay. Right. And what we're interested in is solving for the deformations or the displacements of each of the nodes in the mesh. Okay. And so, the actual problem statement for this example is to use the direct stiffness method to compute all of the nodal displacements in the system. Okay. Oh, we also have, in addition to this, we have F1, F2, F3. Okay. We have also all the nodal forces. Okay. And so the first step in this process is to actually use the element stiffness matrix for each of the springs. Okay. Okay. And so for spring A, we know that spring A has a spring constant of, K sub A. And so let's go ahead and write that out. And actually, we're going to write out the full stiffness system. Right? And so spring A, the left node for spring A is node 1, and the right node for spring A is node 2. Okay. And so we're going to relate this. F1, F2 is equal to Ka minus Ka minus Ka, Ka. And so those are the spring constants for spring A. Okay. They're going to be acting on the displacements D1 and D2. Okay. And then for spring B, we can write out a similar system, but we can see here that spring B is acting on nodes 2 and 3, and so we have to make that adjustment into our stiffness system, right? And so spring B is going to be operating on F2, F3. Okay. Okay. The stiffness matrix is still, KB minus KB minus KB KB. Okay. And this is going to be multiplied by, by the response of element B, and so that's going to be D2, D3. Okay. All right. And so, noting on making note of which nodes that each spring is responsible for is actually really important, because that's going to affect how we assemble everything. Okay. So it seems like a minor step, but it's I think it's probably the step that a lot of people kind of overlook, and it kind of leads to their wrong solution. So make sure that you take note of that. Okay. And it'll become a lot more apparent when we do much more sophisticated systems with a lot more elements. But always take note of where my element is and what nodes that they're actually acting on. All right, any questions on this so far? Okay. All right, and so we basically used the knowledge that we've gained before to write out the elemental systems for element A and element B. Okay, so spring A and spring B, and so that's great. And so now we know how each elemental system is performing. Okay, but it doesn't really help us solve the problem, because or not yet anyway, because even though these springs they have their own properties, they're connected, right? And so they're connected here at this node. And so the behavior of one spring is going to affect the behavior of the other spring. Okay. And so we can't just look at these two systems in isolation. So we have to kind of combine them into one system so that we can actually look at what their interactions are. Okay. And that combination and that that kind of merging together into one system, that's what's known as assembly. Okay. And so in other words, another way to say this is that, ideally what we would like is a single stiffness system that governs this entire system as a whole. Okay. Or in other words, we would like a system like this. And so we have 3 nodes in our system. And so we're going to have 3 equations. Okay. 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 And so we would like a system like this, where we have 3 nodes in our system, and so we want just one, and I'll call it the global system. Okay. Okay. We want a global stiffness system that we can solve for all of the nodal behaviors at once. Okay. And this global system is going to take into account that certain nodes are going to have interactions with multiple elements at once, okay? Which is something that our isolated elemental systems doesn't capture on their own, okay? Okay. And so now the question is, how are we gonna assemble this global system, and so do we have to go through a whole derivation for like a 2-element system, just to kind of get that case? And if that's the case, do we have to come up with a new derivation each time we have a different number of springs for different systems? And so the good part is, we don't have to do that. Okay. And so the way that we're going to assemble the system is to take all of the elemental contributions, or in other words, all the elemental stiffness matrices, and just insert them into the proper spots into the global system. Okay. Okay. And and this is where it's going to be key to make sure we know which nodes that the elements act on. Okay. And so I kind of have a very visual approach to kind of showing this, but the textbook kind of has a very kind of mathematical approach. But and there's nothing wrong with the mathematical approach. I just think it's there's a lot easier way to show it. And so the way I like to think about it is like this. And so we know that our global stiffness system has 3 rows and 3 columns in this case. And so the first row corresponds to D1, second row is D2, third row is D3. Okay. We can also label the columns too, right? And so the columns also are labeled in the same way. And so we have D1 to D3, going from left to right, basically. Okay. The elemental systems are inserted into the places which govern their, let me say this again. So the elemental systems are slotted into the locations on the global stiffness matrix that correspond to what degrees of freedom they act on. Okay. And so to put it plainly, let's take element A, for instance, here. Okay. And so element A, we can see acts on nodes 1 and 2, right? Right. And so that means that in the global system, element A's contributions are going to be in all the slots that govern D1 and D2. Okay. And so if we kind of draw a box just like this, okay. Okay. And so that 2x2 box right there, that's basically the D1, D2 spots in our global system. Okay. Then that's where we're going to insert the contributions from element A. Okay. So let me go ahead and slot those in right now. Okay. And so it's going to look just like that. Okay. Element B, on the other hand, element B, we know acts on nodes 2 and 3. Okay. And so we're going to slot element B into the 2, 3 slots in our global system. Okay. And so where are the 2, 3 slots? And so we can see that 2 and 3 are the second and third columns and the second and third rows. Okay. And so they're going to intersect at those, 2, 3 spots. And so if we can draw another box around this. Okay. Just like that. Okay. And this is where we're going to slot in element B stuff, right? So we have minus KB, and then positive KB. Okay. In the spot where it overlaps with another element, all we have to do is just simply add their values together. Okay. Right. And so in that middle spot in the matrix right there, we have KA plus KB. And so, that's to basically represent the fact that node number 2 is being acted on by elements A and elements B. And so, its effective stiffness is kind of a combination of those two. Okay. And then everywhere else that we don't have any, anything, that's not encompassed by an element stiffness matrix, we're going to put a 0. Okay. And so that's the process of assembly, basically, right? And so after you form all the element stiffness matrices, all you have to do is basically just slot them into the appropriate slots in the global system, and then you have an assembled finite element system. Okay. Any questions on this process here? For this simple system, I think it's a little bit clear, where each of the element stiffness matrices go. But later on, what you'll see is we're going to be working on much bigger systems. And so if you're having trouble determining where the system is supposed to go, I like to use this kind of method, although it's a little bit messy, admittedly, right? And so, let's say that you want to add an element that is contributed to, or that's contributing to nodes 1 and 2, okay? What I like to do is I like to draw a line, find through the rows that I'm going to be, working on, okay? As well as the columns, okay? And wherever these lines intersect, that's where you're going to insert the entries for the element stiffness matrix, okay? It might seem, trivial for this now, but, when we work on, more complicated systems, it'll become a lot more useful in those cases, okay? All right. And so, it seems like we've done it here, right? And so we've taken our element stiffness matrices, we've assembled them into a single global system, and so it seems like we're ready to go, right? Unfortunately, we're not done yet. And so, if you actually try to, take this matrix set of equations and solve for its solution using MATLAB or whatever other tool that you like, you'll find that the answer here is undefined. Okay, and the reason it's undefined is that this matrix is actually symmetric. Okay, and so you can't find you can't use a symmetric matrix for a system of linear equations. And so what do we do here, right? And so we're going to need to modify the system a little bit, before we can actually solve. And the way that we modify the system is through the application of boundary conditions. Okay? And so that's going to be the next stage in the process. Okay. And so what are boundary conditions? And so boundary conditions are basically all the external effects that are acting on your physical system. Okay. And so some examples of external effects are things like constraints, right? And so any external effect that's going to constrain motion, okay? Or any kind of external forces or external loads, those count as boundary conditions, okay? Okay. And so any kind of effect that's kind of external, from the system itself, that's going to affect its behavior, okay? And so there's lots of different ways that we can characterize boundary conditions. If you're coming from 540, I think we use the terms loads and constraints a lot. But for this class, I'm going to use their kind of classical, mathematical definitions, okay? And so there are two types of boundary conditions that we can use, in finite elements. Okay. And so the first type of boundary condition is known as a Dirichlet boundary condition. Okay. Probably named after the dude that formalized the theory, okay? And so a Dirichlet boundary condition, the way we describe it is that it directly specifies the value of the solution variable at a certain location, okay? Okay. And so for our case, where most of the time we're going to be focusing on, at least for this first portion of the class, on structural finite elements, okay? Our solution variable, or our primary solution variable, is displacement, okay? And so any kind of condition that directly specifies the value of the displacement, that's going to count as a Dirichlet boundary condition, okay? Okay. And so the second type of boundary condition is called a Neumann boundary condition. Okay. Again, probably named after the dude that formalized the theory. Okay. I didn't choose these names. I know they're hard to remember, but but I guess we have to give the scientists credit. Okay. And so Neumann boundary conditions, kind of speaking generally, kind of are comprised of any kind of external forcing effects. Okay. Okay. And I put forcing in quotations because it can mean Neumann boundary conditions can be a lot of different things. Okay. And so Neumann boundary conditions are basically effects that don't directly specify the solution variables. Okay. Okay. And so one very common Neumann boundary condition that we'll see is like an applied force, right? And so if you apply a force to an object, a lot of times it's not immediately clear how much is going to displace or deform, right? And so if you take a pen, right, and you apply a force and you try to kind of bend the pen, it's not apparently clear, the relationship between how much force you apply and how much it's actually going to displace, right? And so the force in this case would be characterized as a Neumann boundary condition. Okay. And the reason I'm making this distinction is that the way that we actually treat them mathematically is going to be different. Okay. And so first we're going to go over how we treat Dirichlet boundary conditions. I'll show you what to look out for and how they're actually depicted in a problem like this. And I'll show you how to actually count for that in the global system. Then we'll do the same for the Neumann boundary condition. Okay. But before I do that, are there any questions on this? Okay. All right. So let's kind of return back to our example and look at the kind of the original diagram that we had going for this problem. Okay. All right. And so in the original problem, we had something that looks like this, right? And so this node right here is node 1 that's attached to the wall. Okay. And we had nodes 2 and nodes 3. And of course, we have KA, KB. Okay. Let me focus on node 1 first, right? Okay. So node 1 is fixed to the wall, right? And so if something is fixed, we basically say it's not going to be deforming at all. Okay. And so basically we can kind of conclude already from the beginning that the displacement at node 1 is going to be 0, because it's fixed to the wall. Okay. Or in other words, mathematically, we can just do this. And so D1 is equal to 0. Okay. And so since we're directly specifying the value of the displacement at this node, just kind of based on its condition, we can conclude already that this is a Dirichlet boundary condition. Right? Because again, it's a direct specification of what that displacement should be. Okay. Okay. And so for a Dirichlet boundary condition, the way that we handle this mathematically is we basically take this condition right here and turn it into a form that we can plug into the global system. Okay. Okay. And so how are we going to do that, right? And so we basically just have D1 is equal to 0. Well, let me put it in this form. Okay. And so instead of just having D1 is equal to 0, let me do something really weird. Okay, so let me do this. Let me turn it into like a vector equation, right? And so if we have, this form of this equation where we have 1, 0, 0 as a row vector multiplied by the column vector d1, d2, d3, right? And set that equal to 0, we can see that, if we actually perform the vector multiplication here, this is equivalent to that, right? It's just kind of a long kind of way to do that. And so why would I do this? Why would I go through the trouble of taking such a nice simple equation right here and expanding it into, something that requires, literally 4 times as much writing? Well, when I put this equation in this format, this is very similar to, how we format our global system, right? And so what if we take this equation and then pop it into our global system, instead of one of the equations that we have there, okay? And so basically, when you have a Dirichlet boundary condition, you're going to use that to replace an entire row in the global system. Okay. Okay. And the row that we're going to replace corresponds to the one where the boundary condition is actually applied. Okay. And so since this Dirichlet boundary condition is being applied on node 1, we're going to replace the entire first row of the matrix. Okay. Okay. And so I'll show you what that looks like visually on the next page. But before I do that, are there any questions on this? Okay. All right, so let's go ahead and see what that looks like visually on the next page. Okay. All right. And so I'm actually going to write out the original global system first, just so that you can actually see me replace it in real time. Okay. Okay. All right, so this is our original system, right? But we just got done saying that, because there's a Dirichlet boundary condition applied on node 1, let's look at the row that corresponds to row 1 right here. Okay. And now let's actually replace this with our Dirichlet boundary condition, right? And so let's look at our Dirichlet boundary condition again, right? And so you can see that the coefficients that we have for the first row is going to be 1, 0, 0, right? And then on the other side of the equation, we have another 0, right? And so let's go ahead and replace that. And so instead of Ka and minus Ka here, instead of what I have is 1, 0, and there's already a 0 there, but let me write over it just for completeness sake, okay? And then instead of F1, we're just going to put a 0 there. And so this replacement of the equation is basically our way to implement that Dirichlet boundary condition. Okay. Right. Any questions about how I did that replacement? Okay. All right. So that's Dirichlet boundary conditions, and thankfully that's actually the more difficult to do. And so now let's look at the Neumann boundary condition. Okay. And so remember, Neumann boundary conditions, they correspond to any kind of external forcing that we're applying on this system, okay? In this particular example, we only have one instance where we're applying external forcing, and that's on node 3, right? And so on node 3 here, you can see that we're applying an external force of F, okay? And so the way that we apply this, this Neumann boundary condition is to say that, we're applying a force F on node 3, and so let's just say that F3 is equal to big F, okay? That's it. And so we can see here in this system, we have an F3 right here, right? And so let's just replace that value with big F. Okay. Right. And thankfully, that's all you basically have to do. Okay. And the last thing you can do, before we solve it is just to recognize that, on node 2, we don't have any Dirichlet boundary condition. We don't have any external force. And so all we have to do here is just write a 0 in for that. Okay. And so after you apply those boundary conditions, okay, now our system is ready to solve. Okay. And so we have 3 equations and 3 unknowns, although, technically one of the unknowns is really easy because D1 just equal to 0. And so in principle, we have 2 equations and the 2 unknowns, okay? And so, because this is a relatively simple example, you can probably do this one by hand, and it's not going to be too much trouble. But traditionally, what we do is, once we kind of get the equations in this form into this kind of matrix set of linear equations, this is when we kind of pass it off to the computer and have them solve it, okay? And so most of the time in this class, I would only ask you to get the system to this point, right? And so I would only ask you to, just to derive basically the global linear system of equations. And then to actually get the solution, you would actually just solve it in MATLAB. Okay. And later on, we'll have global systems that are like, 6 by 6, 9 by 9, sometimes, 24 by 24, right? And so, I'm not going to stop you. If you really enjoy solving linear system equations, then, all power to you. I'm not into that stuff personally, and so, I don't partake. But if you want to solve those systems, hey, go for it. But I think the easier way to do that is just to punch it into MATLAB, punch that linear system into MATLAB, and just let MATLAB solve it for you, because it's going to be a million times faster. Okay. All right, and so that's the whole process. And so today we went through the entire finite element process. We did element stiffness matrix, we did assembly, we just did boundary conditions, and then once you apply the boundary conditions, you can solve in MATLAB. Okay. And so, we're just about out of time today, but I do have one more example. And so when we start class on Monday, I'll go ahead and do that example, which kind of just shows you this entire process again, but for a more complex example than just 2 springs connected to each other. Okay. And we'll see how that goes. And then from there, we're going to hop on to truss equations. Okay. And so any questions on any of this before we wrap it up for the week? Okay, all right. And so that's all we got time for today. So thank you everyone for tuning in. Remember, starting on Monday, I will be in the classroom. And so if you want to, attend class in person, I will be there physically. And so our room is CS 309. And so that's on the 3rd floor of the CS building. But again, you are free to continue participating in the lectures virtually. So I'm going to be streaming everything on Zoom, just like I have been. Okay. All right, so thank you very much for, oh, what's up?
Yeah, quick question. So for the exam, so are we gonna set up the problem just like this and then not solve the linear system, or are we gonna be able to use MATLAB in class and solve it?
No. So I have confidence that you can type things into MATLAB, and so like for the exams, it would look just like this, and so you would basically stop right here, where you would set up the linear system, and then that would be it. Yeah.
All right, cool. Thank you.
Yep. All right, so thank you everybody for tuning in this week, and so I hope you guys enjoy the rest of your weekend, and I will see you on Monday. So some of you in person if you want to attend. So have a great weekend, everybody.
Thanks, Professor. Have a good weekend.
Thanks, you too.
Have a good one, Dr. Tran. Happy belated Lunar New Year.
Oh,
Yes.
thank you, thank you. Oh, did you guys want to see my cat? I promised you guys I would show you my cat, just to prove to you.
Always, always.
All right, let me get her. All right, here she is. This is Angel Meow Meow, perfectly happy. Although she
She's
wants to
probably
get down.
pissed off that you picked her up. Yeah, definitely. Have you seen that documentary, Don't Fuck with Cats?
I disturbed her nap. Usually after she
Yeah, it looks like you did.
after she eats, she likes to yell a little bit and then she likes to sleep. And so, but
Have
yeah.
you seen the documentary, Don't Fuck with Cats?
No, I haven't, but it sounds like I should.
You should watch it. It's pretty crazy.
All right, say bye, Angel. It's the last time you'll ever see them.
Bye. All right, Dr. Tran. See you on Monday.
All right, see you Monday, Kamal.
Good night.
Good night.
See you Monday, Professor.
Carlos, Ryan, did you have any final questions? Okay, all right, I'll see you around.